Good?
Yeah, so hello everyone and welcome to the first NetSeminar for 2013. Our speaker today is Dave Taht. Dave co-founded the Bufferbloat Project, which many of you might experience while you try to Skype when the Roblox is syncing or you're doing other stuff at your home. He has a very long story in things that combine Linux, embedded systems, networking, wireless, etc. He has done this from multiple perspectives. The most interesting that I found was that he went for 3 years in Nicaragua and he worked in wireless mesh networking, IPv6, and things like this. And today he's going to talk about a joint work with Kathleen Nichols and Van Jacobson on how we can get rid of bufferbloat in our router.
Oh. Thank you. Is anyone from the class of, what is it, CS 244 here? Right? Excellent. I'm under the impression that there's a project due on the 5th. All right, well, I have a prize for you guys for the best one. So, as you said, I'm Dave Taht. I'm one of the many, many people working on CODL and FQCODL and derivatives and trying to reduce the bufferbloat problem. We are gifted today by two other really talented folks. Eric Dumazet, who's the author of FQCODL, as well as the insanely great polisher of the CODL code in Linux kernel. And we're also gifted by, oh, and I just forgot, Luigi Rizzo, who is an author of a fair queuing scheduler called QFQ. He's also working hard on some interesting stuff above that, besides things like Net, this DD thing.
NetMap. NetMap, right.
So, we've been working on fixing bufferbloat aggressively for the last 2 years. We have finally come up with a combination of two ideas simultaneously that appear to reduce the bufferbloat problem on edge devices by a rather large amount. The first portion is CODL, and that is an algorithm developed to manage the length of queues going out over an interface. And it is TCP friendly. It does a really wonderful job of cutting the size of queues. And simultaneously, Eric Dumazet has worked on a version of stochastic fair queuing, which gives you the ability to manage multiple flows in a very fair manner. And the combination of these two things together tastes great. So, I have felt compelled while giving these talks, to try to understand how well my audience actually understands the core concepts involved. And if I can get the right answer to this question, I can speed through a whole bunch of slides and move forward. So, who in the room thinks that TCP Slow Start increases the transmission rate of packets linearly in response to acknowledgments? How about the other way? Raise your hands one way or the other. So those of you that know, you think that B is the right answer, and those of you that don't know didn't answer either way. Well, the correct answer is it's exponential. And this means that I'm going to have to go a little more slowly than I would like. So what we're seeing with the bufferbloat phenomenon is that as rates went up, we needed to add additional buffering to be able to handle higher speeds. And unfortunately, we added excessive buffering at nearly every layer of the stack. For the last 2 years, Eric Dumazet and other members of the Linux networking group, as well as around the world, have been smashing buffers wherever they could find them that were excessive. And the second problem is that until we actually did that, you could turn on any one of these cool new algorithms and whatever, and nothing would happen, because there's all this stuff buried deep in the stack. And I like to think that it's mostly fixed on Ethernet now, at least in the Linux kernel. It's fixed in ADSL, we're good. Wi-Fi, major problem. And things like LTE network, still a major problem. So you can tweak these algorithms, but you have to fix the underlying stuff to handle control. Now, I've been dinged a little bit lately. I really only care about the edge of the network. I don't really care about what happens in the data center. The guys in the data center have to deal with nanoseconds. And I care about seconds. So these differences in orders of magnitude, if I can fix the internet out here, the data center can take care of itself. So TCP 101, this is a slide I always feel compelled to do. TCP's behavior. This here is slow start. It's not slow, it's exponential. It's the very first thing that happens with the TCP stream. It happens really, really fast. It ramps up really, really fast as a function of RTT. And then it goes into congestion avoidance mode. And then a packet is dropped here. And then it cuts in half. A packet's dropped there, cuts in half. Until it finds an ultimately benign rate for the overall sharing of the link. But over here is a little slow start thing. Without a packet loss or a packet mark, TCP doesn't know what to do. If you don't drop any packets, it will expand to use all the bandwidth that's ever possible and eventually drop a packet. Long after you've blown up your link in your life, there's an RFC called RFC 970 about that. Going back to buffering, a little bit is good. More than a little bit just adds delay. But we don't know what the right length should be. It's highly variable. We're looking at bandwidth between a K or 10K or 100K. Typical speeds across the world are in the range of about 100K to 10 megabits for uplinks. We have almost all of our hardware here is capable of gig E, so that's 2 more orders of magnitude. And on top of that, you have 10 gig E and upcoming 100 gig E. So somehow we have to have one internet that works well across all these bandwidths. There's a lot of optimizations, things like IW10. Anybody know what that is? You don't know how to say. No?
The initial windows in 10?
Yes. And what that does is that means it's the rate of the increase of slow start. It starts out a lot bigger and gets bigger a lot faster.
You actually didn't answer your second question, which is when do you stop slow start? And I believe that's when you reach an arbitrary threshold.
SS threshold.
Yeah.
Yes. Okay. So I got a couple experts in the room. So, not knowing this, we started coming up with a bunch of algorithms in the early 90s, things like red, blue, to try to come up with a way of managing the queue length in relation to the actual bandwidth being used by it. That would let us handle these differences in bandwidth. And a whole bunch of terms came out of that. TCP elephants, mice, and ants. Now, ants is actually a new term, but I'll get to that. A TCP elephant is a flow that gets out of slow start and into congestion avoidance, but while it's doing that, it's still ramping up, trying to find the right bandwidth, always probing, try to find what the right bandwidth against all the other streams that are on the path. TCP mice, it turns out that there's no formal definition of that. The one I've been using is that a TCP mouse is something that never gets out of slow start. It's a web page. It's a teeny little something. And it just stops. You don't ever see a sawtooth. I'll get that in a second. And the last one is what we've been calling ants. And these are just itty-bitty little packets that are kind of important. DHCP, without which you don't get an address. NTP, without which you don't get time. DNS, without which you can't turn something from a name into a number. These are all teeny little packets, and they're statistically important. If you lose one, bad things happen. And I'm just going to skip right to the next slide. I think I lost it. Oh well, I'm ahead of it. We'll talk to that point in a second. So after FQCODL was developed, CODL was developed at the ship, the ACMQ article went out. I got caught up on sleep. Eric got caught up in sleep, and then on a Saturday wrote FQCODL, put that in the Linux kernel the same day. And we said, aha, Bufferbloat is solved. And we waited for everybody to turn it on to play it. Not a lot happened for a while. But it has been incorporated into a bunch of versions of Linux. It'll be part of Ubuntu 12.4, for example, in a couple of weeks. It's part of Linux kernel, etc. We're doing good. But what I've discovered is that once we had cut latencies by such a huge amount, it became really hard to understand what things looked like. And we started working on a string of tests that would let us see in the real world what we had accomplished, or what we could accomplish, or where we maybe had gone wrong. And the specification is called rule. And without the specification, I had difficulties in trying to get a single stream in the real world, talk to a server somewhere else, and keep the buffers saturated so that we could actually see the behavior of the algorithm. So I ended up increasing the number of flows to 4 up and 4 down, which has been proven to work very well between all the way up to about 160 ms of round trip time between my box and somewhere else. So on top of that, hey, I had 8 streams. Why don't see if diffserv actually works somewhere? So turn that on. And now that we had this standard pattern, we went and we looked at how IPv4 and IPv6 would compete in this environment. How differently would they behave? 6 to 4, various other forms of path measurement. And we looked at fairness. TCP flow from Timbuktu versus TCP flow from fairly nearby should ultimately, someday, share almost the same amount of bandwidth in the pipe. Does that really happen? No, I don't.
Why do you think why do you think that's the case? I mean, isn't it?
I don't think it's the case.
I mean, isn't it sort of well known that TCP throughput is sort of in some sense inversely proportional to latency?
It is closely related to that, yes. Turned out to be easy to look at, though. So what the heck? I also wanted to look at various and sundry other forms of TCP, notably Reno, Leadbat, and Westwood, which are delay sensitive TCPs that are supposed to also coexist with normal TCPs. So a couple other simpler tests are in it. And this is what the result looks like. I'm going to refer back to these graphs over the course of this talk several times. So these are 4 different colors of 4 different TCPs up, or sorry, down, 4 different TCPs up, and a simultaneous ping measurement using both ping and UDP, also classified, to see how much latency is being induced on the link by all these streams. So this is taken against a Comcast link rated at 24 megabits down and 8 up. And you'll note that despite that rating, it's how fast is it really running? You can see that due to the buffering, you can see that the TCP sawtooth itself is really elongated, and you can see different streams taking over back and forth here. Similarly, also related to buffering, you see the sawtooth taking 30 seconds in this particular case. You can also see that because these things are changing size, there doesn't appear to be any classification on this particular link. So the reason why it was there is, how do you see the effects of the queuing algorithm on a loaded network, on admission control, on mice and ants versus the elephants? Remember when I was pointing to slow start? How many elephants do you see? I mean, this is an elephant, this is an elephant, this is an elephant, this is an elephant. Most of these are mice. Or ants, you can't tell. And you can't tell what the effect on the user is by looking at a plot like this. There's no, what level of latency was incurred by this elephant being right here. How much link did that eat?
What's your y-axis?
You know, I don't know. The paper's right there. I believe this is over time, over that particular second. This is each second. These are all the simultaneous flows existing in that particular fragment of the second.
Is it count?
I believe it's a packet count, I believe, yes.
A packet count, not a flow count, or?
Packets. Each of these are flows. Okay?
So one understands it all.
I put a link up earlier on. That's one of the papers. So, moving on. 2 papers came out recently. They were both really good. Mark Almond's paper, Comments on Bufferbloat. He was trying to sense from the center of his system, connected by GIGI to a bunch of experimental residences, what the residential latencies really were. And those residences weren't experiencing any latency, but the connections from those residences to other residences over the internet were. And he found that roughly 5% of those connections were exhibiting added delays. Another paper by Dario Rossi, measuring lead-back traffic, passive background measurement, said, 1% seeing bad latency. The thing is that web traffic consists of hundreds of connections, and you can shoot yourself in the foot. So if you have one of those connections experiencing bad latency, your experience of clicking on that website, a video fails to load, an image fails to load, it takes a while. So if you have an average of 1% failure rate distributed across 200 connections, you're going to have problems. So I'm going to skip that one. The core part is that DNS web traffic in particular has a whole bunch of web lookups. If there's a buffer in the way, those DNS lookups are slow. The TCP SIMs slow down. Slow start gets slowed down. And trying to find an optimal flow rate takes a really long time. This is a plot taken from my testbed over in Los Gatos. Same connection as before. Same rating on the line as before. It's 8 meg. One thing I failed to point out, since this is 4 streams, the average should be what your actual bandwidth is, barring other traffic. So this is 8 megabits up, and it's impossible to tell what it is down. So the next step, after loading up a link with this stuff, was to hit it with other kinds of traffic. And I've run so many different kinds of web pages through the Chrome benchmark so far that I can actually tell by looking at the pattern of which website I'm looking at against this constant noise of the actual transaction. This over here is one of the most incredibly sharded websites in the world called 163.com. Feel free to download it and wait 16 seconds or so for the whole thing to come down. And over here was Xfinity, one of Comcast's sites. But this was after I applied FQCODL to the system. So you'll note that I have a nice average here. By the way, this blue line here is just an artifact of the bug in the plot. This is Slow Start doing some interesting things, but that's just an artifact. So we achieved, I was simultaneously running another rule test at the same time, so I achieved roughly half of the total bandwidth available. And over here, you see the TCP Sawtooth doing well. In addition to this, there's also a shaper in play. So I'm looking at background traffic, eating just a little bit of the background. And I'm really happy that I didn't really kill all the elephants. I shot a whole bunch of elephants. They just dropped a little bit of bandwidth. The web page loaded. They came back. Web page loaded. They came back. They came back. So, elephants are alive. My favorite part of this one, though, is this. We went in the previous thing here, where latency grew from here to 250 ms to where it only oscillated roughly 7 ms back and forth. This is well within the tolerances of most games. Certainly, human beings really hear and feel latencies about 10 ms or so, almost invisible. So this is the part I'm really happy about that. Without running web pages, this is what the tape prototype looks like. Again, what it does here is it treats background traffic at about 20% of the load max, doesn't optimize for VI, video, or best effort, and gives EF packets, which are usually used for voice, a pretty big boost, but it still limits that to roughly 30%. Not particularly happy about the overall latency swings, but kind of hard to complain about getting down to 10 ms worth of reduced latency rather than hundreds or thousands. So I'm kind of, go ahead.
The queues of your device, do you have a drop tail or do you have a red turnout? What do you expect red will behave in a
all these examples are using a derivative of FQCODL called NFQCODL or FQCODL itself. It is drop head using fair queuing and the CODL algorithm to shorten lengths of the queues.
But I was just wondering, as a comparison, you could have
this
turned
here?
on red and see how it behaves.
You're perfectly welcome to download the test and try. So this here is just P FIFO fast, standard drop tail. out of the box.
So drop down.
Kind of links
So,
through.
and what's your maximum queue size there?
In this particular case, it's 1,000. But in this case, what's happening here is that the buffering is actually mostly occurring in the CMTS and in the cable modem itself, not in my own device.
Okay.
So I don't have a lot of insight as to what's going on there, except that it's possible to improve it considerably.
Okay. Since you mentioned a new algorithm, so I was just wondering that because red could just help here already. Because
Well,
you have a queue and then you have, you limit your minimum maximum threshold and then they're going to settle down at so any kind of basic state-of-the-art AQM might be able to help you here already.
I am certain that any state-of-the-art AQM would help here, yes.
Okay.
It may not do as well on the latency side, and it may not do as well on TCP admission control, and a few other things. But I certainly have published the specification and the code in the hope that people will try algorithms such as Red and Pi, and possibly I hear a rumor that Eric's working on something new. No. QFQ, I've tried QFQ plus column. There's all kinds of possible solutions to these problems.
You can download it from Bufferbloat.net.
Sorry?
You can download the code from Bufferbloat.net.
Well, the FQ coddle code is actually on the Linux kernel.
Right, except for the test.
The test itself, I have a link for it.
Okay, great.
If you Google for netperf-wrappers, you'll find it there. Okay, so I'm very happy. This is, if you look at the timestamps here, see if I have the right timestamp. There's one at 12:50, taken from the same location. I turned this stuff on at 12:01. I went from unbelievable latency to almost zero latency swings, as well as a dramatic increase of available bandwidth. Lastly,
How do you measure the rate of the flow?
the rate of the flows is being measured by taking a sample on currently I believe it's 100 ms interval from the output of the netperf tool. It's built into the netperf wrappers. We are actually not measuring doing packet captures. This is a user space tool. So, lastly, in the last couple of years, video traffic has become very common, and instead of using a standard like RTP or something like that to distribute it, what we ended up doing is having used TCP for it. And what happens in the case of Netflix is every 10 seconds they issue a GET, and they pull down a new copy of the buffered copy of the video as fast as they possibly can. And then if it completes in under 10 seconds, great, they'll do it again and again and again for the course of the video. So you see these enormous spikes for a brief period, over and over again, when you're looking at video traffic. This does kind of interesting things to voice over IP and so on that kind of would like to have some buffer space to themselves. Some other plots using a tool called TCP Trace and xplot.org, showing the overall behavior of what is a classic video stream. And Kathy, ladies and gentlemen, Kathy is the co-author of How Algorithm. So, I mentioned TCP Fairness. I agree with you. It hasn't really been fair. This is a way to see how fair it might actually be. I went and I looked at FQ coddle plus the cake shaper against sites that were, this one here is in Redwood City, this one over here is in New Jersey, this one here is in Denmark, and I went and I looked to see if these sawtooths would ultimately become fair. And it actually turned out that they came really close, even over these long RTTs. Happy about that. Oh, while I'm at it, I'm okay on time. Things like these two spikes here. At the time I was testing a new version of FQ coddle, I was like, oh my gosh, what went wrong here? Wow. I must have a bug in my code. Well, no. Or a bug in the algorithm. Well, no. When you're doing these kinds of experiments, it helps to be aware of all the variables involved. It turned out in this case that I plugged into a new network that had a ton of IPv6 traffic. Now, when a certain kind of IPv6 traffic came on, it caused an instruction trap in this thing, which basically knocked it off the network for about that long. And instead of working on finishing what I've been calling cake. I've spent the last 3 weeks killing every last darn instruction track in this because it messed up my data. But you got to be careful about other sources of experimental error. So I have tons of other data sets. I know this talk is about CODL or FPCODL, but if I can encourage you to try this particular test, a bunch of any kind of traffic against any algorithm that you might have at hand, have fun. So, Kathy and Van spent about 14 years trying to come up with a successor to Red.
Not every minute.
Yeah, every day. Brains to the grindstone. Exploring various sundry ideas. Trying to come up with something that was CPU efficient, that did a good job, that was gentle on the network and wouldn't cause any real bandwidth hits, but try to reduce the overall latency induced by TCP flows to a bare minimum. And it turned out that, when did you publish the ACO article? June?
April-ish.
April? Yeah.
The paper version, I think, came from June.
So they came up with an incredibly elegant and simple algorithm that has some really beautiful core ideas that are so far have not been terribly well expressed, and my mission today is to try to do so and have Kathy correct me when I'm wrong. So the first thing is, I'm going to just talk to this slide. Every time a packet enters the system, it is time-stamped. And it then egresses the system, and if that egress is lower than the target delay for the system, there's nothing. It just lets it go by. It keeps time-stamping and looking and time-stamping and looking and time-stamping. And so long as we're below target for that particular stream, it just lets it go by. When it finally exceeds target, Carl says, aha, we might have a problem. But it doesn't do anything. It goes to sleep for an interval. And it just keeps time-stamping and marking, time-stamping, keeps checking the time, and it waits for an interval to go by, which by default is 100 ms, before it decides to invoke what I've been calling the drop scheduler. And at this point, at 100 ms, it drops a packet. Now, if you drop one packet from a TCP flow, what happens? To the rate. What happens to the rate? Sorry? You drop one packet from the flow, the rate will ultimately have when that signal reaches the other end. But you don't know how long that's going to take. You don't know where the other end is. What happens if you drop two packets from a flow inside of a single round trip time but not together? Anybody know? No?
It depends.
It depends.
Depends on whether you're running SAT or which version of TCP.
What happens to the rate?
What?
What happens to the rate?
Well, I'd be very careful about calling it rate. I'd say the number of the window size that you pump out there, but some of them, if you drop two within too close together, they'll go way back and a couple.
Okay. Well, by and large, if you drop more than one packet inside of an RTT, not a whole lot happens. It's just that first drop that actually is meaningful. So if you decided to arbitrarily just start dropping packets here to get into the target, that'd be any good. So Colin just drops a packet, and then it takes the interval and applies inverse square root to it. So instead of 100 ms, you cut it by just a small amount. And we just keep watching the flow. Timestamp, check the timestamp, to egress, to entry, over and over again, and we say, oh, we hit another interval, and it's time to drop another packet. It could be that that other system is so far away, 183, 183, it still hasn't got the signal yet. Or it could be unresponsive, we don't know. So drop another packet. Maybe the time drops a little bit, but it still hasn't dropped below target, so we decrease the interval just a little bit more, drop another packet. During this time, I could be sending anywhere between 1 and hundreds of packets in this particular flow. It doesn't matter. It's just trying to provide a signaling mechanism. We keep shrinking the interval until we reach a point where we start seeing the amount of time spent over the target interval go down. We don't do anything with that currently. It goes down. Finally, after dropping a couple packets in the flow drops below the target. And so long as there's always a packet in the queue, we still never drop. We drop out of the dropping drop scheduler. So now we've found in Cuddle what could be the RTT. It could be the sum of a whole bunch of different RTTs. We don't know. It could be some of the different RTTs compared to all the different flows that are in the system. Don't have enough information about that. All we care about is that, yay, we're below target and we don't need to shoot any more packets.
How do you set the target?
That was arbitrary value, chosen by experiment.
No, there's actually, I think Van explains it pretty nicely in the talk he gave at the IETF. Some of the numbers are the kind of stuff we did look at 14 years ago, but then we did a bunch of experimentation with it too. But it's to maximize, or sort of maximize, get the most throughput you can get without increasing the delay very much. And like Van likes to look at everything based on what if you were only running a single TCP through, because that's kind of like the worst case, because if you drop it, if you have a couple things sharing the link, then lots of stuff is going to be there. So there's kind of a curve of this sort of power of the throughput divided by delay, and trying to pick about where that starts to fall off is the way that you come up with that. And the way he did it on the plots, he looked at a Reno TCP, which is kind of pessimal because the, what's the name of the Linux one? Cubic is much better at using up the link. And then you get so it comes out that, like, say, between about 5 to 10% of that, of the RTT would be the right place to do it. But of course, we don't know what the RTT is, but kind of looking at typical ones. But we kind of worked between like 5 and 10 milliseconds. And actually, initially, Van argued a lot for 10 milliseconds, but the more we did with like simulations and different traffic, it seemed like it made more sense to push it to 5 because you really didn't lose much of anything, and it was much better for delay. I mean, we wanted to keep the delay as low as possible, like the standing delay, not the,
So it's a function of RTT, or?
It's kind of, it is a function of RTT, but if you say, like, if you look at the plot, right, like a good place to be is at like 5 to 10% of RTT. And then if you figure, well, RTTs are usually what, like, 30 to 150. I mean, there's sort of like a sweet spot, and then there's the outliers. And so 5 milliseconds works out pretty good. So it's a combination of analysis and just like running stuff and saying that works. It seems like it works pretty good. The weakest link here is the interval and not knowing the RTT, and that's where, if anybody's going to do any further work, I would encourage trying to figure out an intelligent way to be more independent, or at least sort of figure out the interval. And in fact, we have to be really careful here because our friends at Cable Labs, they're putting in more delay than that sort of 100 milliseconds that we baked in, and that's why they were getting bad behavior. You have to make sure that it's okay if your interval is shorter than some of your RTTs, but it should be kind of like longer than your usual one. I would, like whatever 80th, 90th percentile should be under that.
So the RTT includes everything apart from your local buffer that you're running Cuddle?
Yeah, I mean, the thing is, because you're trying to see if there's a response to that drop, you are going to end up taking in, if you end up sitting behind other stuff in buffers, it's going to raise your RTT. But if you're personally running Cuddle on your buffer, then you shouldn't have too much of that problem. But one of the things, like with cable stuff and satellite stuff, if you've got like request and grant type systems, you're going to put some more delay in there, and you need to add that to the RTT, the sort of physical RTT, right? These are some things that actually could stand to do more work. And actually, I have lots of things that people could do that would make nice little projects, but as I don't have time to do them. But and all you need is a simulator and a brain. Yeah.
Sorry, Shuttle. Just to make sure that I'm understanding this correct. Where exactly is the algorithm running? Is it in the router? Is it in the host? Or where do you expect this to run?
In this particular example, it would be helpful if it ran in the router the most,
Okay.
as well as on the head end.
You must run it on the congestion point where you have a queue.
Yes.
If there is no queue, you can't do anything. So
But if there's no queue, it won't come on.
Yeah.
But, you know,
obviously, this is the point where you have a queue.
Okay. So I figured I was going to pretty much spend the whole talk on this slide and may have that still happen. There's another phase in the cutoff. And that's what we have gone through this first process here of trying to find what we think might be an optimum dropping point. And we now have the stream under control. We spend some time when the stream is under control, and it might briefly pop above target, but if it doesn't stay above there, Kyle will just keep going. But if it stays above target for long enough, it tries to remember the last drop interval in the drop scheduler, and it tries to resume that in at least 5 different variants now.
Yeah, well, unfortunately, that's kind of, it's, the idea is sound, but I think the implementation sucks. to be honest.
So it's count -2 in one version of the algorithm, count -1 in another version of the algorithm. The current NS2 model actually invokes the control law again in an interesting way, and to try to combine what's the real RTT, or is this a sum of the RTTs to get there. So while you pointed to intervals being one of the most problematic ones, I looked at the resumption of CODL
So
as
I
being one
just
of the
found
earliest.
something out, I don't know whether, that, so part of the reason we think the problem is there, so I just didn't realize this till I was really looking at the code like 2 days ago, and so there's this idea that if you have, you said if you have a packet left, well, it's not a show. If you have a packet left in the queue, you don't want to drop, but what it really is if you have an MTU's worth of bytes, right? Because we discovered that, especially with webs and stuff, you can really pose your utilization. So what I did originally, when I was like hacking this into the code, was I inhibited the dropping state, like what did you call, when you go into the dropping algorithm. So if the queue was too low, I just inhibited it and didn't do the drop. But when Van was compressing the code, he changed that to you come out of the drop state. And I think it didn't really sink into me until I was looking at the code the other day. I think that was a mistake. And we talked about it, and he thinks it was a mistake too, but I haven't done enough. I've only started doing some runs. But I think that might solve, we think that might solve some of the problems.
One of the variants I have of NFQ CODL actually does not do an MTU. It will go down to the actual minimum packet size seen in the queue. Rather than stopping at an MTU, it goes all the way down. We're trying to apply to the fair queuing variant.
The minimum, but if you're doing fair queuing, then it's different, right? I think then it's just that you don't want to, if you drop, you can go ahead and drop the last packet as long as it's.
So as you can see, it's an area of active research. The source code is out there. Please try it. Because even with the bugs that we're aware of, it's really wonderful, as I showed you from some of the slides earlier today, in terms of reducing outliers and latency. So we just went through a Q&A session. Kathy, I hope you don't mind my picture here. I like to think it's a pretty nice pony. So, any further questions before I try to spend a few minutes on the fair queuing component?
Sort of the Achilles heel of this is that it has to be implemented in some core internet router somewhere that you have no control over.
It's being implemented on the edge. The best place to put it would be on cable modems, VSLAMs, CMTSs, various edge devices. Doesn't need to be edge core.
Because you can actually just generate obvious on the edge, just like Nana said with because if you just fill up your cable modem pipe.
I'm getting ahead of myself. So I use a software rate limiter called HTV that will take, move all the buffer to your own device. So you're not a prisoner of either your modem provider or the CSON guy. If you move the control to your own device, and all these algorithms work great. And all the plots I showed you, we're using an HTV thing on one of these things. They're about $100. I mentioned that the project there is called SarahWork.
The key thing though is that you can basically saturate your uplink and downlink through your cable DSL node. Well, I guess you have to do that pretty much in general. But there is this interesting thing that in many cases the edge actually isn't the bottleneck, because I have 802.11n Wi-Fi, right?
This talk is not going to be about Wi-Fi. I have a separate talk on that one.
So wait, are you saying that 802.11 and Wi-Fi are the bottleneck?
It's like they're not. Like I have a 100. So I can't really run this on my laptop because I'm on this 100 megabit Wi-Fi network, right? But it's actually the cable modem is the bottleneck.
Yeah, I will argue that
control the cable modem because it's it's owned by Comcast and they control its firmware.
Again, it helps to have Google stuff in there. One of the things that we've been working towards is getting stuff like FG column and derivatives into the cable modems by the standard. So we hope inside of a few years that
But I think what you're saying is interesting too, which is that you seem to be saying that you can sort of create another bottleneck by putting a box in front of the cable modem, which could potentially manage it. That's an interesting idea.
There are people who do that, right? I mean,
anybody sane should be doing it.
Yeah.
So please do that.
Or you could put it in, or it could be built into your Wi-Fi router.
Yes. So this is built into the SarahWork project, which is OpenWork firmware. I've had a lot of flack about people saying, "Oh, you can't implement CODL or FQCODL in hardware." I'm sorry. I believe it's totally doable to implement it in some kinds of hardware. This kind in particular. This is a really cool board called a Z board. There's a neat project here at Stanford called NetFPGA, which has a lot of really great open code for implementing algorithms. I would love to find somebody working on an NetFPGA project that would play with this. This is Cat's Pajamas. It's my hope to try to be able to build our own Ethernet chip that implements the stuff at its very core, so that the fair tuning component and the CODL component happen in nanoseconds. Okay. I have 5 minutes left to talk. Haven't had a chance to point out the known flaws in CODL. It's a single queue. It works well with streams that are TCP friendly. If you hit it with a ping flood, if you hit it with something that's not responsive, bad things happen. So having one queue in this particular case does not help. We have a big problem in that there are multiple versions out there. All the source code's available, but we have just slightly different versions working on the two research topics that were mentioned earlier, and encouraging people to come and help. If you already have some latency in the queue, it doesn't do a whole lot for ants and things in slow start. Takes bursts. So the last piece, I have a paper on this one, is that all the attempts at building delay-based TCPs, things like leadbat, which is also kind of known as BitTorrent, don't work anymore because they're all using enormous, by CODL standards, latencies of 100 ms or more to determine their own drop strategy. So, next question. What would CODL do against a stream that's currently in slow start? A lot. CODL may have achieved an optimum drop rate for the existing stuff. It doesn't have tachyons, it doesn't know. So you'll see streams building up, and because it's being very gentle about its drop strategy, it's not going to react really quick. It's going to take some time. When we said, Kathy and Dan said in their wonderful article about CODL, it's just a piece of the solution, Bufferbloat. The next piece, not just in mitigating slow start, but in offering lower latency and fairness, are derived from a string of fairness queuing algorithms. WFQ, SFQ, QFQ. We looked really hard at QFQ in the beginning. Eric worked really hard on bringing the stochastic fair queuing algorithm, in particular in Linux, up to where it could possibly handle a range of bandwidth from its original, 1 megabit or so, up to tens of gigabits. And along the way, I'm really low on time, improved dramatically when we started running into elephant problems again, because you can sort through all of your additional many flows, but you still have an elephant flow, it'll still eat the whole buffer, you had to manage it somewhere. So he got really hot on an algorithm called ARED, and it came up with one of the first hybrid stochastic fair queuing algorithms, combining both the concepts of stochastic fair queuing and the RED algorithm in the hope that we would have an answer. And it really worked well. It's in the Linux kernel. Please try it. If you're going to try just plain RED, please take a look at SFQ RED and ARED. Maybe there's some good ideas in there. It turned out to be really hard. Sorry, sir.
A quick question. So I think Eric mentioned you need to run Codel at the condition point.
Yes.
This sort of maybe silly question, but so, and you said that you need to deploy this at the edge, right? Like in the home router.
Yes.
So are you deploying this at the egress or the egress queue?
Yes. Both of
Yes,
those.
both of them.
Both.
Yes.
Because okay.
So you have to have an inbound rate limiter and an outbound rate limiter to control both queues.
But in Linux, is it? I thought it was only possible to police ingress queues.
It is possible.
Yeah.
You have to use IFB.
It's called the intermediate functional device, intermediate functional block, right? IFB. So you turn that on. There, example code out there. You turn.
It's a bit complex, but it's doable.
Yes.
Just,
Yes, sir.
Just
So
Google it.
one of the problems that we've seen is that it's not just the queuing discipline that you will use, but it's also the fact that you have multiple buffers in your router or in your device. You have something that runs on the queue disk level, and you might do perfect scheduling there. But the moment that you will throw this into your driver, it has a 50 or 100 packets buffer there and introduces a huge latency. So I'm wondering, because it seems to me that this SFQ happens at the queue disk level, and so what have you done with the buffer below?
We have a thing called byte queue limits now, and this handles there's three different things here. One is called byte queue limits. That basically manages the size of the TX ring on the devices themselves, and I usually talk about that. I tried to skip it and I hope I fit the talk in. And what that tries to do is just keep just enough packets in the kernel level to not hit interrupts too hard and to keep the device busy. So it's got just enough buffering to keep stuff going into the device. We came up with cut over an order or two of magnitude of additional buffering at the bottom of the stack by using that. However, when we're talking about using the artificial software rate limiting, none of that comes into play. If you have a 100 megabit device and you're sending data out at 20 megabits, the buffer's always empty. The buffer accumulates in the software rate limiter, which could be HTB or HFSC, or just a straight token bucket, and that's usually one packet and one packet deep. It works really well. Okay. So I was really pleased when Van gave his talk and he said all these lovely things about FQCombo. He said it provides great isolation. If you have low-rate video conferencing, low-rate web traffic, they never get dropped. Kyle never even sees it. And they get priority access in the queues, so there's almost zero latency for them. IW10, an enormous burst of packets. If you have it on your inbound, they get spread out across the rest of your load, so it takes a missile of packets and turns it into buckshot. You get massive improvements in utilization. We've seen bidirectional utilization improvements in the 35% range just by turning it on, even on normal networks, not on your bottleneck link. Mixing up the packets helps all of the streams increase in flow and reduces the number of drops that you see in a single stream. And he said, we're sticking code in the boxes. Deploy Kalo, don't do that. Deploy FQCombo, it's just across the board win. And I sat there in the audience and blushed. I didn't have a whole lot to do with FQCombo itself. I was there.
Yeah, but I think the thing, and we're seeing it right now, right, is that if you, well, now you agree, right, that you can have too many queues for the amount of bandwidth you have, which is ban things. There's probably an analytic way to do that. It's just another good project.
Yes, thank you. Can I try to talk to it a little better? All right, so FQCODL is designed by Eric over there. It works all the way up to 10 gig E, or beyond, I don't know, whatever you can tell me. It works down pretty well too. It has a few problems at lower bandwidths that we've been encountering. And it comes by default with 1024 queues, which seems like it's a really good number. If that's a thing about the birthday problem in there, and how you can isolate all these DNS flows and ant traffic with mice and your elephants. And it turned out that when we're working at lower bandwidths, that having so many bloody queues, 1024 by default, it was possible to have the scheduling algorithm dominate over what CODL was capable of doing, given its bottommost minimal limits. So I reran all of my benchmarks, all those pictures you see there, using 16 and 32 queues at lower bandwidths. And it worked marvelously well. So it may be that there is a function that describes the number of queues that is optimal for your bandwidth.
Are you saying just the overhead of the algorithm became too high, or what was the problem?
There's no overhead.
It's the, there's another problem too, right? If there's too many bins, you end up with a big queue again, essentially.
Yeah.
I mean, if 1024 packets is too many for your
I call it the horizontal standing queue problem. Okay, so you
What
used
are
to
all
have
those
standing
queues
queues.
empty, so there's an introducible, I mean, I guess I don't understand.
That's right. You used to have a vertical standing queue problem, which is what CODL was designed to do. It tries to reduce your vertical standing queue to 5 ms from whatever it is, but it allows for bursts. Then we introduced SFQ CODL, which means that the vast majority of the streams never develop a queue. That's really good for them. But it's now possible to get to where you have a horizontal standing queue. If you saturate, if you try to put 64,000 TCP streams or 1,024 TCP streams, you'll end up with one packet each lodged in each CODL queue. And if, say you're running at 1 megabit, that's 13 ms. So if I have 1,000 of those, I've now got my buffering problem back again.
But hold on a sec. Why is that bad? I mean, in some sense, you're doing. It seems you really are fairly allocating your resources here, and you're also interleaving the flows, so you're evening it out. And you're getting where the person is. That seems good.
It's good. Yes.
So there's a couple.
You really want 13 seconds of induced delay?
I was just going to say, I think I know, I haven't completely checked this out, but I think I know what's going on in the case that Nicolette was talking about, which is that, yeah, they've got 1024 queues, and they're only running a maximum of 164 flows, so they probably aren't all active at the same time. But I don't know, maybe it's easier to draw a picture. So they do this thing where they're running these voice emulations, and they're trying to see how good they are, and then periodically they start up trying to do get a web page. And their model for this is that you're opening like 24 connections all at once. So I think what's happening there is then, they've got all these queues, right? They've got 1024, and so the CDRs are kind of going along, the voices, are like this, and they're getting great service, and all of a sudden all this new stuff bursts in, and it's new, right? So it all gets a queue, and then the way that the FQ-CODL works is that the new stuff goes first, right? So now all of a sudden all those voices get pushed down, and you're going to go boom, 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 all the way down through all of those little web things, and all of a sudden all these guys get pushed down, and by the time you get to them, they might get dropped.
But
that's just sort of a...
What's the alternative to basically, kill the new flows or delete them or whatever?
No, the alternative is not to have so bloody many queues, right? I mean, it's too many for the link. It should be that you need to work out the right dynamics.
So, but this seems because it's not weighted for queuing. You would really like some kind of weighted for queuing.
Oh, it's not. So
SFQ is stochastic for queuing. Everyone has the same weight.
Okay, sorry.
Yeah, we have a problem. Stochastic for queuing is not fair queuing.
Oh, okay, now I understand. Yeah,
One of the things that I have experimented with is Luigi has a lovely, interesting algorithm called QFQ. And we have implemented Coddle itself as a separate algorithm, so it's possible to use a whole bunch of QFQ style bins and combine that with Coddle bins. The thing that I run into is that one of the beauties of FQ Coddle is that it will use very little memory. And if I use sufficient queues per QFQ Coddle thing, this guy here will run out of memory. So I would love to see a merger of Coddle plus QFQ that was, Coddle plus QFQ that was cool.
Yeah, so the real problem is starvation in the stochastic fair queuing.
There's also another alternative in this problem, is that now that we have two a scheduling mechanism and a drop strategy built into the same code, it's possible to say, oh, well, maybe I should go shoot a different packet with a different Coddle queue when I'm under this kind of condition. Or maybe I can measure the increase of delay across the number of flows I have and shoot a couple other flows randomly, or not so randomly, or some other algorithm. It's really interesting stuff. I hope that we can find something that will work better across the data ranges of things there. I didn't want to take away from one thing, I'm also all way over time. Over the last 2 years, we have cut the amount of buffering that is in the Linux kernel, which is used by a lot of router products, used almost everywhere on the internet. From where we were seeing tens of seconds of delay, this is at 100 megabit, you're seeing 130 ms worth of delay, I believe. To when we added BQL in, at 10 megabit, we were seeing 70 ms delay, again, the order of magnitude worse than 100 megabits. To where we added FQ Coddle, and we got it to where you saw between competing streams 13 ms worth of delay here. This red line is a ping. This is there. The other beautiful thing about adding these algorithms in this fairness and the queue management is that you see streams almost immediately acquire just the right amount of bandwidth without oscillating around a lot. Whereas here, you can see the effects of a standard drop tail queue.
So, Dave, is this with the TCP small queues enabled, or is that
I don't remember. I try to timestamp my graphs. Another one of Eric's innovations after doing all this stuff, he added to the host side a wonderful new feature called TCP Small Queues. This stuff works really good on hosts. It really does. So TCP Small Queues, as well as another optimization, lets you run this stuff to where it only will keep a tiny portion of the queue full and measure from the internal measurement from the TCP stack to there. So there's 4 layers of buffering that have all been wiped out from the Linux kernel starting with Linux 3.5. So it's good stuff. There's another really cool optimization in FQ Coddle. We may get a chance to talk about it. But if you actually can't get TCP admission, a flow admission into an FQ Coddle queue, it signals the stack without dropping to reduce its suggestion window. Neat trick. So encourage people. There are people out there. This was someone playing with DSL, the IP Fire guys. They went from observing 1.2 ms worth of induced latency under load to 0.2. I've shown you a whole bunch of other graphs and charts and slides and pictures with circles and arrows and the stuff in the back as to how far we've come. I don't think there's a really long, far way to go. My primary mission in life is to convince people to go play with it, to implement it on their own systems, to try it on switches, to try it at home, to try it on large scale, small scale, on large number of users, and get back to us and see what goes right and what goes wrong. Moving forward, I'm so much out of time. We are on a quest for a full-blown replacement for the standard queuing mechanism in the Linux kernel. I'm working on what I've been calling Cake. I have heard a rumor that Eric was working on something similar. We are getting such much better results than pFIFO fast. It would be great to be able to replace it on everything inside of a year. See better network performance for everybody. Software rate limiting. I remember Eric over there telling me, oh, that was about 9 months ago. Ongoing enhancements to Coddle and FQ Coddle. Because the delay-based metric seems to work so well, other people are taking older ideas like the idea of a Pi controller, and Cisco came out with something called Pi. I haven't seen it yet, looking forward to seeing it, so don't know. Trying to find, maybe I'll hit that. What is the relationship between fair queuing and different forms of route mechanisms? Cool. Trying to get better tests so we can look at this stuff in finer detail. I'm pointing to the rule test. There's a bunch of papers coming out. One of the hard problems is that I've had two separate hardware vendors tell me, all of our entire packet flow model and our next generation of home routers is baked into the hardware. We can't fix it or change it. That makes me really grumpy. So I would like people to try pouring these algorithms in the hardware. If I have to do it myself, I will, but I would like to find somebody else to do it. Okay. Lastly, working with the IATF, the standards bodies, large companies, ISPs, to try to get these core improvements into the onto the edge of the network so that nobody has to do any configuration, it just goes on by default. And I'm not going to talk about code. Lastly, Wi-Fi. Giving a separate talk on this one. Wi-Fi remains a really major problem, and we think some of the problems are intractable. But we're looking at 7 seconds worth of delay there on a particular network I was at recently, and so on. So, now that I'm done at 15 minutes over, any questions?
Time for 2 questions.
No? You ready to go home and turn us on your own stuff?
So for multiple
something you were saying
TCP
you turn
strings,
Sorry?
For multiple TCP strings, the fairness issue. I mean, because currently the FQ model is implemented in routers, right, and cable and modem. I mean, it's basically in the IP layer, but TCP. I mean, if your laptop launch multiple TCP, one is from the cable, the cable modem with FQ model. Another one is from the modem without FQ model. So I mean a fairness issue, because in FQ model, if we drop some packets based on the delay in the router itself, right? But this one, it doesn't have any limitation. So I mean the fairness for these two.
Let me go back to one of my earlier slides, okay? I'm not quite sure of the context of your question. This is an existing cable modem, an existing cable network.
Mm-hmm.
The throughput on this particular cable modem, without any form of sharing, without any form of just standard drop tail behavior, was about 1/2 to 1/3 of what I achieved. Oops, this one. Using a combination of moving a buffer to the device itself and applying FQ column. The reason for that is because lower latency allows the TCP signaling to take place much faster.
Okay, yeah. So I mean, now forget.
You're not necessarily getting less rate, right? You're causing less delay for yourself.
Yeah, but I mean, forget the short-term TCP traffic. Okay, so two long-term traffic, they compete with caudal and without caudal.
Yes.
So, and especially in a slow start issue, right? I mean, in the face of slow start, and if this TCP is the packet dropped by the modem during the phase of slow start, this one will not have this issue. And then, I mean, the TCP backup in the TCP layer, it will drop like currently IW is 10, and then, for example, at IW is 20, it back off to 3 or 4, and the other one will increase, I mean, without any backup, okay? Then, I mean, how these two TCP flow can compete fairly?
I'm still not really.
I don't really understand the point. You are saying that the one flow is coming through one FQDL and another one is not coming.
Right. I mean, now like
So
your laptop,
path, so
your laptop have two AP to connection. I mean, two. One is from the, for example, AP1, VAP1, another VAP2, And this AP has FQ caudal. This one has no FQ caudal. But I mean, you put two string to this to the IP layer. I mean, so FQ caudal. If FQ caudal drops some packets, then this TCP string will be in suffer.
So first of all, it shouldn't drop in slow start, right? Because you saw those pictures, and the other time is that maybe we're not making this clear enough, but you're still getting good throughput, right? I mean, that's the rate that you see on these flows aren't getting different rates and not getting different throughputs on their wire. One of them is building up this big backlog, so when it puts packets in, it has to wait, and the other one they're going out. I don't know what's...
I know. I mean, caudal can make sure the latency is low and at the same time maintain the throughput.
Yes.
Maintain the rate. But I mean, the results is from single TCP traffic or multiple.
Multiple.
We've done
Multiple. Or a number of flows, TCP friendly stuff.
Okay.
So we've tried single TCPs all the way up to hundreds. Also kind of different algorithms.
When I developed the FQ caudal, I was using 200 multiple TCP flows in my test.
Okay. Yeah, then it's clear. And another issue, and currently I read two very recent papers talking about the Bufferbloat. One is from SICOM Communication Review, and actually they have a big data set, and they analyze the trace, and then, I mean, argue that Bufferbloat problem actually is not a serious problem in daily life.
You're talking about Mark Almond's paper.
But that's kind of
right, exactly.
But it doesn't really, it doesn't really matter, right? I mean,
Yeah.
I think that like Mark Almond makes a good
Yeah,
argument. But I don't
I'm
think
not
people should
saying
be
the work
changing-
is.
People should run out and be
Right.
changing the TCP protocol because they think there's a problem, especially because all you need to do is deploy something that manages the buffers. If there's no buffer, the AQM is never going to come on, right? So that's the perfect solution because you don't want to change protocols. That's stupid, but there's a lot of people out there who want to, they want to go to standards bodies and they want somebody to pay for it, and that's what they want to do. They don't care about fixing the problem. But I think it's true. It may not. We don't know how big of a problem it is, but we do know it's a big problem some places.
Right,
And
exactly.
So we're coming up with things that fix the problem.
In your group, any work or ongoing work, you give the answer directly to people. How much and how often you guys are influenced by Bufferbloat?
It's one of those, I am a musician, or I like to think I am, okay? And I personally am sensitive, so the drummer's here, I'm playing bass over here. This is roughly 4 feet away, that's 4 ms. Okay? Sorry?
Or 8 round trip from when you play the bass to when you hear it from the amp.
A little bit too much of a heat. I can stand this far away from the drummer and be playing good music. If I get out 8 ms, it starts getting hard. I actually have to look at the drummer rather than hear him. And if I get 20 or 30, I'm just not good enough to get that any further away than this. Now, humans are very, very, very sensitive to response times. We can hear something that's off by 5 to 10 ms. We're also very sensitive to jitter. So when you click on something, you generally expect that it's going to take the same amount of time when you click on it one time as the next. And when it doesn't happen, it's very upsetting. You find people, my favorite one is when you go to the elevator, you push your button. The next person comes in and he pushes their button because that's going to work better.
I understand that.
So,
yeah, but just like Mark's work, do you have the ongoing work to answer? What's the percent?
So, guys, because we're running quite long, can you take this offline?
Okay.
Okay? You don't mind? Thank you very much.
Thank you. Thanks for having me. Before you turn it off, don't turn it off on that slide. I put the slides up on the first page of the slide. That's one of my favorite ones. Good? All right. Low latency is good.